All right, so now we're going to look at the taxonomy of generative graph neural networks, which was presented in this paper. So you guys will find the references, all references at the end of the PDF of this lecture. So here you can see there are so many methodologies for deep graph generation. It's a very hot topic, and it's a very I would say it's a highly expansive research topic. And here you have different categorizations, and I really like this kind of taxonomy that was presented in this survey paper published in 2023. And today we're going to look at a few examples. So we can't cover all of these. If you guys are interested to expand your knowledge, feel free to look at the paper. And there are other papers also that you can explore. I would recommend you starting with review papers and survey papers that kind of present the whole field and the different methodologies. So here today, according to this paper, there are different categorizations of and subcategorization of deep graph generation models. And first, we have the first layer or the first level that categorizes these models into unconditional generation. So we have unconditional models right here. And we have also conditional models, conditional generation. So under the unconditional generation, we have what we call the one-shot generating or one-shot generation. So we're going to look at the example of adjacency matrix based one-shot generation today. And we're going to look also quickly at the sequential generation or sequentially generating graphs. So you have 4 subtypes. You have the node sequence, you have the edge sequence, you have the motif sequence, and you have the rule sequence. Okay, so 4 subtypes. So we're going to go over them very quickly, just to give you an overview. As I said, this lecture is about presenting the landscape of deep graph generation. And at last, so for the conditional generation, we're going to look at 2 examples. So conditional generation conditioning, we have 3 types: sequence, context, and graphs. So we will look at the conditioning on graphs, okay? And then we have the edge, 2 simple examples: edge transformation and node edge co-transformation, okay? So here you can see what is highlighted in red. It means that we're going to cover it. We're going to go over it today. So that's our roadmap. So quickly, let's start with the unconditional generation. And for the unconditional generation, sequentially generating a graph. So the inputs here, as you guys can see. So what I want you to think about is, of course, you can read papers that worked on these problems, and you can find existing source codes. There are so many references in the survey, but the idea that every time I present something to you, I would like you to think about how to leverage what we have learned in terms of message passing, node update rule, propagation on graphs, to do this kind of sequential learning, right? And you need to keep in mind that some maybe properties you want to stipulate, such as invariances and equivariances. So these are things that you can explore, of course, at a higher level. But now let's start with very simple things. So first, what we have as input. So this is our input node. So we have an input node to our network, and the network will learn, or the GNN that we will design here, that is designed here, will learn how to generate nodes in a sequential manner. So first, we have the node V1, okay? So that's our input node. It doesn't have any edges. And then we're going to add another node, so node 2. So here we added node 2. So V2 is added, and we added V2, and we connected it to node 1. So we created an edge, E1, 2. Now next, these 2 would have been generated. So now they're colored in gray, right? So this is the generated part already in the previous step. And now we need to add a third node, so another node. So to add this node, we need to learn how to connect it. So if we can connect the node only to, for example, 1, so we can have a node here 3, or we can connect it to only, node 2, or we can connect it to both. So here, for example, when we added this, of course, it's learnable. So we need to optimize a particular loss, right, to learn how to generate this properly. And this is generated not in a random way, but in an optimal way to optimize our target loss function that we have, okay? So here we added our V3, and we connected it to our two nodes. So we add the node and also its edges. So every time you add a node, you add its edges. So if it's not connected to a particular other node, so that's 0, it means the edge is 0. So every time you add a node, you need to add the edges connected to that node. All right. Now for V4, you guys can see here, we're going to add another node, and you can see that V4 is connected to only nodes 2 and 3. So you can create its vector. So this is V4. And V4, if you look at 1, 2, 3, 4, so its connectivity vector in our adjacency matrix will be 0, 1, 1, and here, if without self-connectivity, it's 0. Okay, cool. So this is node sequence-based generation. It's unconditional because we don't have any target graph here. Okay, so in this case, we don't have a target graph to predict. It's also based on self-supervision. It could be based on without any conditioning, self-supervision, or unsupervised. But the term unconditional here is a bit, as I said, in the categorization of the paper, problematic. It doesn't always imply, does not always imply that we are in a fully unsupervised framework. Okay, it doesn't always imply that. So sometimes you can have, some conditioning on a particular context or particular not label. I mean, you can have unconditional generation. The conditioning will be on a particular additional information, which means you can do supervised, but you don't have that additional condition. So there are different terminologies. I don't want to confuse you guys, but here, let's say mostly, we would assume that unconditional is unsupervised. Okay, so mostly. So that was just between parentheses. So now let's look at the second example. So edge sequence base. So in the edge sequence base, we start with the edge. Okay, so we have the edge. We know we have an edge that connects nodes 1 and 2. So we create the edge. We know it's connecting these two nodes, 1 and 2. All right. So here I know my edge connects these two nodes. Next, I'm going to add another edge. So here we add another edge, E13. So the edge, of course, needs to connect to one. So here in this example, it connects sequential. So it connects to one of these nodes. Okay. So 1, 3. So we added this E13, right? And it connects these two nodes, 1 and 3. And then we will keep on doing that. So basically sequentially. So here we have added 1, 4. So that's our new edge that we added, and it now connects, it adds a node 4, so with it, but the focus is on the edge. So these two are actually quite similar, but it depends whether you want to focus on the edge generation first or the node generation first, right? So you focus on the edge generation, so you define the edge, and then you add the nodes, define edge, add nodes, or define node, add edges. All right, so that's very easy, I think. And then, for example, here we get the final graph. So you can see we added a node 2, and this node 2 is connected to 3. Okay, so sorry, we added node here. We added edge 2, 3. Okay, so now we're adding edges between these existing nodes. So we added this edge that is right there. Okay, so there are different ways of defining this. So in edge sequence base, there are so many algorithms, so many approaches. You can condition, you can guide your edge sequence generation according to some rules you define. So it's very, I would say there are lots of options and different algorithms that you can explore. And this is just, the basic ideas. First, to kind of, add the edge, and then do connect these nodes, or keep on adding nodes, or connect existing nodes. Like here, for example, you connect existing nodes. So these are, let me write it here, connect existing nodes. And here, for example, add a new node with the edge, because it's not, because V3 does not exist, okay? So it wasn't there. So yeah, so now the third one is motif sequence based. So the motif sequence based, it means we add blocks of subgraphs. So it's kind of also simple. So instead of generating one node at a time, one edge at a time, now we generate a subgraph at a time or a motif at a time. And here, for example, we started with this, a motif C1. So this is the input motif, right? C1. And then we added a C2, so a second motif here. So we connected it. So you connect a whole block to the original, the previous motif. So here, if you use gray, so this is our motif, and we need to create the connection. So created two connections here, and we need to learn how to connect. Okay, so that's the key challenge. Now, for example, now we have a motif 3. So the motif 3 is this block. So we added this block, and now you can see that this block, we connected it only to node 1. Okay, so we could have connected it differently. And remember, this is an optimization process, so you need to learn how to connect. It's a learnable process. And that's the goal of this, is to learn how to connect these motifs, right? And yeah, so now we have, for example, here, another motif 4. So it has 3 connected nodes. So now C4 is connected to 1 also. And you can see how we generated the whole graph, the final graph, as a bulk of, or a concatenation of different motifs, all right? So this is the graph here. So if you guys can see it, all right, here we go. All right, cool. So now the rule sequence based is a bit more context or domain specific. So if you have particular, for example, if you want to generate particular molecules or biological entities, or you have some rules about the graph topology that you want to stipulate, so you can do that. So for example, here you can start with a node and say add branched atom. So this will give you a ring. So construct the ring, right? Make the atom as C, so you add the C inside the atom, right? So we're constructing atoms here, and then add a single bond, add single bonds between these. So this is, for example, these are rules that we define, and by following these rules, we can generate or upgrade the graph and keep on adding more elements and more specifications. Okay,